In this video, we solve problem 12.5.078 from the Larson and Edwards Calculus Early Transcendental Functions test, 7th edition. We're asked to use theorem 12.10 to find the tangential and normal components of acceleration for each curve given by a vector valued function. So we have this vector valued function in A and this vector valued function in B. Since this is a linear combination of I hat and j hat, this is a curve, or the curve that corresponds to this vector valued function is a curve in the plane. This one has an x component, a y component, and a z component. So this is in 3-dimensional space instead of 2-dimensional space. Now I gave you different formulas for a sub t and a sub n than the ones that they're recommending you use here. So what I'm going to do is I'm going to show you how to use the formulas that they are referencing with this theorem 12.10. And I'm also going to show you how to use the other formulas. So theorem 12.10 says this. It says if r is a position function, then the acceleration can be written as this function times t hat plus this function times n hat. This function that's multiplying t hat is what we call a sub t. That's the tangential component of acceleration. That's the part of the acceleration that is in the direction of motion, or potentially in the opposite direction of motion. It's the part of the acceleration that's parallel to that line of motion. And then this part is the part of the acceleration that is perpendicular to the direction of motion. It always points in the direction that you're turning. So what they're asking you to do when they ask you to use theorem 12.10 to find these is they're asking you to use this as your formula for a sub t. So that's the second derivative of position with respect to time. And they want you to use this for your formula for a sub n, the normal component of acceleration. That's curvature times the derivative of position with respect to time, or not position, I'm sorry, length or distance traveled along the curve with respect to time squared. I was saying this was position, but that's not position. R of t is a vector, that's position. This is actually distance traveled along the curve. So this is a second derivative of distance traveled along the curve with respect to time, or the first derivative of speed, not the first derivative of velocity. Okay, so if I want to use these formulas to solve this problem, and that's what I'm going to do. I'm going to use these formulas first, and then I'll use the formulas that we talked about. I need to first rewrite this formula in terms of r of t, because we're given r of t, we're not given s of t. Once we do this rewrite, it's going to be really obvious what you're supposed to do. Because we know that a sub t is the second derivative of the change in position with change in distance traveled along the curve, excuse me, whoops, with respect to time. This is speed. It's not velocity, it's speed, because we're talking about change in distance per unit time, not change in position per unit time. This is not dr dt, it's ds dt. And ds dt, that's speed. Speed can be found this way. First you find the velocity, then you find its magnitude, and then you take the derivative. So even though they gave us this formula, I would prefer that you take that and you rewrite it as this formula, and then this formula will tell you exactly what to do. That's what this is, what that means. So if I want to compute a sub t using the formula that they referenced, I would first rewrite it this way, and then I would just do what this formula tells me to do. First, I want to find the velocity vector. Then I want to find the speed, which is the magnitude of the velocity. And then we want to look at how speed is changing with respect to time by just taking the derivative of that result that you just got from right there in that step. Okay, so our r of t, has components 9t squared and 9t minus 3t cubed. So when I compute r prime, I just compute it pretty easily by computing the derivative term by, or component by component. So we bring the power down, multiply by t to the 1 less power. The derivative of a constant times t is just the constant. Over here, you bring the constant down, then you bring the power down, you multiply by t to the 1 less power. So you have 18 minus 18t times I hat plus 9 minus 9t squared times j hat. Now notice that both of these components have a factor of 9 in them. So I would suggest factoring that out. So now we have this. So now when I want to find the magnitude of this, I can use this fact. The magnitude of a scalar times a vector function is just the magnitude of the scalar times the magnitude of the vector function. And I used r of t, maybe I should have used u of t. That's just for vector functions in general. So when I want to find the magnitude of this now, so that I'm finding the speed, it's just going to be the magnitude of, or the absolute value of 9, which is just 9, times the magnitude of this vector. And finding the magnitude of this vector is pretty straightforward. You take the components, you just square them and add them and take the square root. And this is what we get. So we have 4t squared here. This is 1 minus t squared times 1 minus t squared. If you write that twice in FOIL, you'll have 1 minus t squared is minus 2t squared, and negative t squared times negative t squared is positive t to the 4th. And the positive 4t squared and the negative 2t squared simplifies to a positive 2t squared. And hopefully that leads you to think about factoring this. I want you to remember where this came from. It came from taking this 1 minus t squared, and squaring it. Because that was a minus, I had a negative 2t squared here. If that was a plus, I would have had a positive 2t squared here. So if this factors in this way, I bet this factors as 1 plus t squared times 1 plus t squared. And that means it's a perfect square, and that means we can simplify it. Or if I put my t to the 4th first, I could write it like that. Check, first times first is t to the 4th, outer times outer and inner times inner is a positive 2t squared, and last times last is a 1. So we have this. T squared plus 1 is always positive, so the square root of something squared when that something is positive is just that something that you started with. So we just have 9 times the quantity t squared plus 1, or if you want, you could distribute that 9. So we have found the velocity, and we found the speed, and now we want to compute the derivative of speed. A sub t is the derivative of that with respect to time, which is 18t. Not too bad. That's one way of finding a sub t. Now, the method that I recommended for finding a sub t is a little different. But you could use this method as well. If this is your acceleration vector, thinking of it as being split into 2 components. One is a sub t times t hat, and perpendicular to that is a sub n times n hat. the magnitude of this vector is just the magnitude of this, because t hat is just 1 unit long, right? The magnitude of this vector is just a sub n. So this squared plus this squared equals this squared. It's just a right triangle. Now, if I am trying to find a sub t, and I know the acceleration vector and the tangent vector, or excuse me, and I know the magnitude of the acceleration vector, a sub t, that's the magnitude of this side, or let's just say the absolute value of a sub t is going to be given by the hypotenuse. And since this is the adjacent side next to theta, but not the hypotenuse, we're going to have that times cosine of theta. And if the angle is acute, this is positive. If the angle is obtuse, this number is negative. So we can drop the absolute values where the sine of cosine of theta will take care of the sine of a sub t. So that's one way of doing it, but we don't know theta. So we could multiply this by the magnitude of t hat and divide by the magnitude of t hat. And the reason we do that is now this numerator looks like our formula for the dot product of the acceleration vector and t hat. And we know that the magnitude of our unit tangent vector is just 1, because that's what makes it the unit tangent. Oops, actually, I don't even need the absolute value there, sorry. Because we don't need the absolute value here. So if I want a sub t, this is the formula that I would typically use. So we have our position vector. This says compute the acceleration vector. Velocity is the derivative of position. Acceleration is the derivative of velocity. And then we need to take this and dot it with t hat. Well, t hat is given by r prime over the magnitude of r prime. Or if you prefer, you could call that the velocity over the magnitude of the velocity, or the speed. If I factor out a 9 from here, we get this. We have 9 times 2t and 1 minus t squared. So the magnitude of this just comes from taking that 9, which is a scalar. You take the absolute value of the scalar. In this case, the absolute value of 9 is just 9. And you take these components, you square them and add them and take the square root. And then you have that velocity vector in the numerator. And the 9s reduce. And now you're here. Now that denominator, that magnitude of the velocity, which we're calling speed, is the same as what we got last time with that other formula. If we write this twice in FOIL, we get this, which simplifies to this, which simplifies to this. And so we just get t squared plus 1. I did that kind of fast because we have already done it. So in that case, we've got this vector with these two components, and we're dividing by t squared plus 1. That means I need to take each component separately and divide it by t squared plus 1. And that is my tangential, or that is t hat here. Now, if I'm using this formula, after I compute acceleration, and then I compute t hat, Then we have to take the dot product of those. And I think you can see that this time, this formula is more tedious. The other formula was much more efficient. Once we took this and rewrote it in this way, we got here pretty quickly to 18t. We should still get 18t using this method. Let's see. When we take a and dot it with t hat, we're taking the x component of a and multiplying it by the x component of t hat. So we're going to have 18 times that 2t in the numerator, which is going to give us 36t over t squared plus 1. And then we want to add, remember that's how dot products work, the y component times the y component. So if I distribute that negative 18t to this 1 minus t squared, I'll have negative 18t plus 18t cubed all over t squared plus 1. Okay, now we just simplify. The denominators are the same, so you can just add the numerators. 36t minus 18t is 18t. So we're here. You might factor out an 18t, and then you have 1 plus t squared in the numerator. That works out. And you get that a dotted with t hat is 18t, so that's our tangential component of acceleration. So this time, this method was a little faster. Now, we also want to find the normal component of acceleration. And we'll use two methods for that. The first method will be using that formula that they gave us. So they said using theorem 1210, which is this, a sub n is the curvature times the speed squared, or you might prefer to write it this way. You take the speed and then you square it there, and then you multiply by curvature. Then you have to remember the formula for curvature. Now, since we're dealing with a plane curve with components x of t and y of t, it might make sense to use the curvature formula that involves x of t and y of t. And that curvature formula is this. Got the absolute value of x prime times y double prime minus y prime times x double prime, all divided by this expression here. This is just a special case of the formula that we have for r of t in general, where r of t has three components, x, y, and z. So if I want to use this formula, I need the speed function. We're going to square it. And actually, we already have the speed from up here, so that's good. Then we just need to find the curvature. Well, if I'm using this formula, and there are lots of formulas that we could use, but if I choose to use this one, I really just need to compute x prime and x double prime, y prime and y double prime, and substitute into the formula. So if x of t is 9t squared, x prime is 18t, x double prime is 18. If y of t, that's my y component, is 9t minus 3t cubed, y prime is 9 minus 9t squared, and y double prime is negative 18t. So our curvature in this case, as a function of t, is going to be the absolute value of x prime times y double prime. So it's like you're multiplying like this, a negative 18, or 18t times negative 18t. I'll just write negative 18 squared, t squared. And then we're subtracting y prime times x double prime. It's like that. It's just what you would get from the cross product if your z component was 0, right? Almost looks like we're doing a cross product here. It's kind of because we are, just assuming our third dimension is 0. So we have y prime I said third dimension, I meant third component, times x double prime. And then in the denominator, we've got x prime squared and y prime squared, and we want to raise that to the 3 halves. X prime is 18t, y prime is 9 minus 9t squared. Now let's distribute. So I have a negative 18 squared is 324. And then I have a negative 9 times 18. It's negative 162. And then a negative 9t squared times 18. So that's going to be a positive 162 t squared. All of that is divided by this. And so we have 324 t squared plus this quantity squared. I think I'll factor out that 9 before I square it. So I'll just write that this way. And so then I'm actually going to have a 9 squared here. And the negative 324 plus 162 is negative 162. So we end up with negative 162 minus 162 t squared all over this. And I think I might write this differently again as well, because I know I'm going to have a 9 squared here. This is 18 t squared. So I'll write that as 2 squared times 9 squared times t squared. And then over here I have a 9 squared times a 1 minus t squared quantity squared. And if you want, you could factor out that 162. And what's left is a 1 plus t squared. So you have a negative number times something that's always positive, so its absolute value is just the positive 162 times 1 plus t squared. And then this denominator, it's kind of messy, but we can work it out. If we factor out that 9 squared and that 9 squared, so we're basically factoring out an 81. We've got 81 times 4t to the 4th plus 1 minus, or 4t squared, sorry, plus 1 minus 2t squared plus t to the 4th. All of this is raised to the 3 halves power. And then we've got the same thing over here. And I'm holding this paper in this way, I'm sorry, because it's sort of coming up. Ups, and this is raised to the 3 halves as well. So you want to apply that 3 halves power to this part and this part. Okay, now recognize that when I add these two together, I'm going to have the positive t squared, or positive 2t squared plus 1 plus t to the 4th. So that's that perfect square, 1 plus t squared quantity squared again. It's just a lot of algebra. Okay, now I think we're ready to finally finish this. If you are raising something to the 3 halves power, that means you're just going to take the square root of that something and then cube it. And here we can multiply the exponents. That's actually going to give us a 1 plus t squared. Since it's squared and then raised to the 3 halves, when you multiply them, you're going to be left with a 3rd power there. So this is actually a 9 cubed. So 9 times 9 is 81 times an extra 9. And we're reducing one of these with one of those. And 82 or 81 goes into 162 twice. And so what we end up with is 2 over 9 times the quantity 1 plus t squared quantity squared. All right, that was a lot of simplification, but that's our curvature. So we said we want to use this formula. We're going to find x prime, x double prime, y double prime, substitute into the formula, substitute into the curvature formula and simplify. And then a sub n is the speed squared times curvature. And they've written this differently. They've written this as ds dt, but whenever you see ds dt, think speed, and speed is found that way. Curvature, whoops, was this 2 over 9 times the quantity 1 plus t squared quantity squared. And then speed, let's see, what was speed? It was 1 plus t squared. That works out. So I have a 1 plus t squared quantity squared in the numerator and another one in the denominator, and we just get 2 over 9. Okay, so that's one method of doing. Actually, I think I made a mistake. Now remember, the speed was 9, or the velocity was 9 times this. So the magnitude of this is actually 9 times this. Sorry about that. So we should actually have a 9 here as well. So the 1 plus t squared quantity squared does simplify with this 1 plus t squared quantity squared. And this 9 simplifies with this 9, one of them, and a sub n is 18. It's not 2 over 9. And the reason I caught that was that I looked at WebAssign and I made sure that my answer was correct because it didn't look familiar. And then I knew, I forgot that extra constant. Okay, so that is one way of finding a sub n. The other way to find a sub n is the formula that I suggested in the videos. If you have this triangle, you've got a sub t times t hat on one side and a sub n times n hat on another side. This squared plus this squared equals this squared. And you're talking about the side lengths. Well, the magnitude of this side is a sub t, or it's the absolute value of a sub t. And then this one is the absolute value of a sub n. When you square those numbers, you're going to get the same number, whether those are positive or negative. But this squared plus this squared should equal the hypotenuse squared, and the length of the hypotenuse is the magnitude of the acceleration vector. So another way of finding a sub n is to just use the Pythagorean theorem to state this formula, and then just solve this for a sub n. So we already found a sub t, and we have the acceleration vector a, so we could just find its magnitude, square it, and subtract a sub t squared, and then simplify. And hopefully we get 18. So this is the formula that I would recommend. Let's see if it's easier than coming up with that curvature. Our acceleration vector is right here. It has components 18 and negative 18t. We've already done that. Now, if you want, you can factor out an 18, and you have that. Now, if you want to find the magnitude of A, you take the absolute value of that scalar, and then you multiply by the magnitude of that vector, which just comes from taking the components, squaring them, and adding them, and taking the square root. So what we end up with is 18 times the square root of 1 plus t squared. And then a sub t, recall from our work earlier, A sub t was 18t. So I've got this and I've got this. I can just substitute those into my formula and compute a sub n. So a sub n is the square root of magnitude of a squared minus a sub t squared. So I've got 18 times this square root squared, and we've got 18t squared. So you're gonna have an 18 squared over here times a 1 plus t squared. It's a squaring function and the square root function, they undo each other. And then you're subtracting 18 squared times t squared. Actually, if we distribute now, got 18 squared minus or plus 18 squared times t squared minus 18 squared times t squared. Those guys reduce, and you just have the square root of 18 squared, which is 18. I think in this case, this formula was much faster. But either way, we got an a sub n of 18. So just like I mentioned, you've got multiple ways to find these results to answer these questions. I give you one formula for a sub t and a sub n. The textbook authors were suggesting that you use these formulas instead. And these are not difficult to do as long as you remember that ds dt is actually the speed, that's the magnitude of the velocity vector. But in the first case, the formula that they gave you was easier for a sub t. And the formula that I gave you was harder. In the second case, the formula that I gave you was easier, and the second formula was more challenging to use. And I would say that in general, that doesn't hold. It's going to vary depending on the problem. It really depends on what this ds dt looks like, and it depends on what the acceleration vector looks like. It depends on a lot of things. So you want to be familiar with both. I prefer the formulas that I suggested that you use in the videos, but these work as well, and you're going to get the same answer either way. So let's do the same thing. Let's do it all over again, but this time for this vector valued function, which is in three-dimensional space. So you have r of t is 3t times I hat plus 3t squared times j hat plus 1/2 t squared times k hat. And for our first method, we'll use the formula that they suggested. So we'll use the second derivative of distance traveled along the curve with respect to time, which is the same as the derivative with respect to time of the change in distance with respect to time, which is the same as the derivative of speed. So we need to find velocity, find the magnitude, and then find its derivative. So finding the velocity is not bad. Just take the derivative component by component. So we'll have 3, 6t, and 1/2 times 2 is just going to give us a 1 times t. And then we want the magnitude of that. So you take the components, you square them and add them and take the square root. So we're going to have 9 plus 36t squared plus another t squared. That's 9 plus 37t squared. And then we want to take its derivative with respect to time. So what I would recommend you do in that case is write this square root as a 1/2 power. So you have 9 plus 37t squared raised to the 1/2, and then use the chain rule. So this is our inside function. First, we're going to take the derivative of the outside. So you bring the 1/2 down, you multiply by the inside function to the 1 less power, and then you multiply that by the derivative of the inside. You're going to get 37 times 2t. And I didn't simplify that because I knew that the 2 and the 1/2 would reduce. And so what we get is 37t over the square root of 9 plus 3t squared, or 37t squared, as our a sub t. Oops. Now we could also find the a sub t using the other formula. So we had this option as our first formula. Let's state the other option, our second formula. A sub t is just the signed projection of the acceleration vector onto the unit tangent vector. So if you find acceleration, you find the unit tangent, you compute the dot product, that's going to be your a sub t. And that's not too difficult to do because we've already computed r prime, it was this, and we've already computed the speed, the magnitude of r prime, it was this. So if you put these two pieces together, you can find t hat. It's just velocity divided by the speed. So you take each component, oops, it's a 3. And then you divide by the square root of 9 plus 37t squared. That's your t hat. And we need to dot that with the acceleration vector. Velocity is the first derivative of position, acceleration is the second derivative of position. So you're just going to get 0, 6, and 1. So you're going to take the dot product of this vector with this vector. So remember what you're doing. You're multiplying component by component, and then you're adding. It's this times 0, and then you add. This times 6, and then you add. This times 1, and then you add. So what we end up with is 6 times this fraction, which is 36t over our square root, plus 1t over that square root. That's going to give us 37t over the square root. And the square root happens to be square root of 9 plus 37t squared. So I think in this case, both methods were pretty quick and easy. Either one is fine. Okay. Now for the normal component, you've got two methods. You can use the curvature times the change in distance traveled along the curve with respect to time squared, which remember that is curvature times the speed squared. Or you can use this one, which comes from the Pythagorean Theorem. I think I want to use this one. Look how simple A is. How easy would it be to find the magnitude of the acceleration vector? And then just take that and square it and subtract. So that's what we will do over here. So that's method number 2. So we compute the magnitude of A by taking the components of A, the 0, the 6, and the 1, you square them and add them and take the square root. It's the square root of 37. Then you want to take your magnitude of A and A sub t and substitute them into the formula and simplify. So we have the square root of 37 and we're squaring it. And then the a sub t was this right here. So we have a 37 here, and then we have a 37 squared t squared over 9 plus 37t squared. Probably want to get a common denominator. So this is 37 over 1 times 9 plus 37t squared over 9 plus 37t squared. I think you see we're going to have a 37 times 9. And then we'll have plus 37 squared t squared minus 37 squared t squared. So this will reduce with this. And all you'll have in the numerator is that 37 times 9. And then we'll have the square root of 9 plus 37t squared down here. You could write that as a single radical expression. The square root of 9 is obviously 3. So you can write that this way if you want. So that's one version of the answer. The other option is to find curvature and multiply it by the speed squared. We're going to get to the same place. It's going to take a little bit more to get curvature first. So our curvature formula in terms of r is this. We can just compute the second derivative of r, so that's acceleration. And then we cross it with velocity. And then we divide by that velocity or the speed cubed. Now we already have the speed. It's right here. So we really just need this cross product, and then we need to find its magnitude. It's actually not too bad. So we had r prime was this vector. And we computed our double prime as well. That was our acceleration. Now we want to compute the cross product, and actually I think it's typically written this way, but the magnitude of u cross v is the same as the magnitude of v cross u. So either way is fine. Okay. Now you're going to cross out this row and that column. And then you evaluate this 2 by 2 determinant. You're going to get 6t minus 6t, which is 0, times I hat, plus -1 times the determinant that you get when you cross out this row and this column. So we'll have 3 minus 0 times j hat, plus the determinant that we get when we cross out that row in this column, which is 18 minus 0 times k hat. So we've got a vector with components -3 and 18 in the x or the y and z components. And then we want the magnitude of that. So you just take the components, you square them and add them and take the square root. And I think I'll write the 18 as 3 times 6. So when I square it, I'll have 3 squared times 6 squared. So we have 9 plus 9 times 36. What do you know? That's 9 times 1 plus 36, or 9 times 37. Looking familiar? And then in the denominator, we should have this speed cubed. So curvature is this square root of 9 times 37, all divided by the speed, which was the square root of 9 plus 37 t squared, and then we're cubing that. Square root of 9 is 3. Square root of 37 can't be simplified, so we just leave that alone. And then this is going to give us a 9 plus 37t squared times a square root of 9 plus 37t squared. If you want to simplify, you don't have to. Okay, so we got the curvature by using this formula. We're supposed to take that and multiply by the speed squared. Well, if I take this, which had the speed cubed in the denominator, it's just going to end up being this divided by the speed to the first. Or we can say that a sub n is this curvature times speed squared. And when you take a square root and you square it, that just gets rid of the square root. So this will reduce with this, and we end up in the same place. We end up with 3 times the square root of 37 over 9 plus 37t squared, which is the same thing that we got using this formula, and this was much faster this time. So I think we can see that you have options. There's more than one way to do all of these. These were the formulas recommended by Larson and Edwards, and this is the formula, these geometric formulas, the formulas that I recommend you use. Occasionally, these are going to be a little bit more challenging, but you really never know when you're just looking at the problem. It really depends on what r prime and r double prime look like, the velocity and the acceleration. It's the form of those and how easily the magnitude of r prime or the speed function simplifies that makes the algebra, more or less challenging. So you've got options, and that's how we handle those problems.